hope really gone? We'll see about that.
Hello everyone, my name is Jacek Szymonek and I'm a senior technology programmer at Techland. So, has anyone played Dying Light 2 Stay Human? Raise your hand, please. Oh, that's great. All right. So if you haven't played Dying Light 2 Stay Human yet, it's a first-person open-world cooperative action game. The players take on the role of Aiden, a pilgrim looking for his lost sister and trying to survive in the broken post-apocalyptic city. And the title of this talk is Behavior Places, Breathing Life into the World of Dying Light 2 Stay Human. So I joined Techland short before the production of the game started, and during my 7 years, I was part of a few teams. First, I worked on shipping the Linux port of Dead Island Definitive Edition and on the Nintendo Switch port of Call of Juarez Gunslinger. When I joined the project that became Dying Light 2 Stay Human, I started in the team that created the City Builder tool. You might have heard about this tool on a recent talk from last year by Łukasz Burtka. It's available on YouTube. It's a great talk. And after some time, I moved on to the AI team, where I took part in building the new architecture for C engine. My interest naturally gravitated towards AI animation, so much so that I finally took over the responsibility for our animation technology stack. The agenda for this talk is as follows. I'll start by exploring the project requirements and motivation for creating a new piece of technology. Then I'll explain what exactly behavior places are, and starting with a very simple example, we'll dive deeper and deeper into some of the technical aspects and decisions. We'll take a closer look at the animation graph and other assets. In the meantime, you'll see how our animators and level designers work together to create the life in the city of Villedor. At the end, I'll tell you about the important parts that we've learned as a team and our plans for the future of the system. So let's start with the requirements that we faced for Dying Light 2 Stay Human. The city of Villedor is dead. Mostly, except for safe zones, the human settlements, where life goes on almost as if the apocalypse had never happened. The survivors are building their homes and executing their day-to-day chores. You can observe them interacting with each other or with the environment using their tools. There is a massive variety of behaviors in here. These characters have their own agendas, they react to daytime changes, they randomly choose to act in different places. The perspective of the game is first person, which makes the locations small, tight in space, and the game can also be played online in co-op, which makes it harder to achieve precise movement and animations. So what I've just described was the rough design for our hub locations and the narration that we wanted to convey. So to achieve this, we needed a technology for creating a huge number and variety of dedicated behaviors, and we wanted precise animations, movements, and also interaction with the environment. Here we've got some isolated examples of these behaviors. So reading a book, sweeping the floor, or being held hostage. These are the things that you might find our characters doing in the game. And now let's dive deep and see how we've built what you've just seen. The building block of our hub location is of course an AI agent. Our AIs are defined in terms of their behaviors that they may execute. So let's take for example this AI with 4 behaviors it's a melee fighter. This AI could find themselves in a hub location under the influence of that location logic, and if there are beds in the location and the evening approaches, we would like to see this AI go to sleep. So it knows how to walk up to the bed using the movement behavior, but we need to implement the sleeping behavior. Then let's say we would like for our fighter to go and sharpen their weapon. And again, we would have to implement that behavior in the AI. Now imagine that we would like to create 20 locations and with 20 unique behaviors for each. And that quickly sums up to 400 behaviors, each of them programmed separately, and most of them used in a single place in the entire game. Now, as you can probably tell, this doesn't scale well. We needed to figure out a different, more data-driven solution. So how have we fixed this? First, we made an important distinction, and we divided our behaviors into two types. The ones that we call generic behaviors can be executed anywhere in the world, and they are an integral part of an AI. Scripted behaviors, on the other hand, are usually tied to a specific location and can often be used to interact with the environment. Now, the key difference is that scripted behaviors are defined outside of the AI agent, and this is a very important detail for their scalability. If we take a closer look at these behaviors, each one consists of some logic in code and the animation data specific to that behavior. So as it turns out, when it comes to behaviors which are mostly used for narrative purposes, their logic is very similar. We play animations in a particular sequence. There's nothing really gameplay related going on there, and we can extract common code easily. The only important difference is the animation content, which I've marked there as being injected. And this allowed us to create a generic, data-driven behavior, which may be executed in specific locations. And we call these locations behavior places. Going back to our example AI, we've now managed to pack all the possible location-specific behaviors into one. It solved our scalability problem for the AIs, but we've opened a whole new can of worms by introducing a new type of asset. Now let's take a quick look at the asset workflow relating to behavior places. First, as programmers, created a special prefab. And we've introduced a new asset type called the behavior definition. These assets contain all the behavior configuration and animation data required, and they are created by animators. The level designers create behavior place entities by placing them in a desired location and choosing the desired behavior parameter. The entity uses the new asset that we've introduced to parameterize the AI behavior. This way, the animators can create the definitions in isolation, and level designers can then reuse them in multiple locations in the game. This is a screenshot of our level editor, and these colorful rings, they represent behavior place entities. And as you can see, a lot of them can go into a single location like that. Okay, let's summarize this part. A behavior place in CEngine is an entity without any visible representation, which is configured with a dedicated asset called the behavior definition. It represents the place where AIs can execute a location-specific behavior by using tailored animations and with rich interaction with the environment. Every AI in the game can either search for a place and decide to use it, or AIs can be requested to do so by an external system, for example, our storage system. Now that you know the basics of behavior places and how the users interact with them, let's dive deeper into the animation graph, the state machine and its evolution. And sometimes I'll be using the term animation graph, sometimes state machine. In this context, they represent the same thing. Let's look first at a relatively simple behavior place example. In this clip, we can observe a sequence of animations. First, the character approaches a chair and then sits on it. Then he's sitting for a while, scratching his head, looking around. It might take one or more loops. And then finally, he decides to stand up. So I've counted 3 animations playing in sequence with a loop in between. Here's how the state machine for that would look like. First, we sit on the chair, keep sitting for a while, and then stand up. Easy. Let's look at another example. Here, we wanted the trader to react to player proximity, encouraging them to buy something. And if we approach again, he stands up for us again. The animation state machine for that behavior place would look roughly like this. So we start with the basic sitting loop at the top with entry and exit animation. That's what we've seen before. But when the player is close, there's another loop. It's called trade. We cannot go directly from sit to trade. We need some transitional animations in both directions, one for standing up and one for sitting down. And entering those transitions is guarded by a condition that checks the character's distance to the player. Our state machine got a little complicated, but that is still okay. It's defined in a behavior definition asset, and it can be dynamically injected into the main AI animation graph. When creating a new behavior definition, an animator would most likely choose one of the existing animation graphs as a template. They would clone the asset and then replace the animations. And after about 50 different behavior definitions were created, we noticed that this approach does not really scale. The graph structures, they were duplicated or very similar. We found 3 distinct patterns in the content with only tiny differences. So our memory consumption grew really fast. And also in the early stages of development, we also needed a way to apply a global change to all the graphs, which was a tedious job for so many assets. Because we wanted to support hundreds of behaviors, we decided to separate the graph structure from the animations. So instead of having many almost identical graphs, we tried to collapse them into a one highly configurable graph. We were able to do that because our animation system lets us inject the animations into the states dynamically. And these animations, the animations used in a particular place are set in the definition asset by the animators. Let's examine how we were able to create the common state machine based on our previous example. And so the main state can be thought of as an activity, that's what we called it, that the character performs while executing the behavior. In this case, it's the act of sitting. This state is, of course, looped. And then next, we need a way to get to the pose of the activity from the default standing pose. And during that animation, we say that we enter the behavior place. And like the entry when the behavior place finishes, we need an exit animation to the default pose. What about our example with 2 activities? So the 3 states at the top we've already covered in the previous example. And now let's look at the other looped animation, trade. Because it's looped, we can think of it as another kind of activity, right? And what is left is these 2 states, which are transitional. So they allow us to traverse between the 2 activities. So to make it clear, these two are still states in the state machine. It's that their nature is transitional. There's still an actual blending going on between those states. Since we are injecting each animation just in time when it is needed, the 2 activities become the same configurable state. Well, we can simply collapse them. And the same applies to the transitions. And after all that generalization, we produce this state machine structure. So here's the key takeaway. A behavior place is represented by an animation graph that alternates between looped animations called activities by playing transition animations in between them. So now one question remains. How do we represent the configuration for the state machine? We know that we've got these 2 activities, right? Sitting and trading. And we can enter the behavior place from the external standing pose to the sit state. And we can also exit from that state back to the external standing pose. We are also able to transition between the activities in both directions. As you can see, our configuration can be represented by another type of graph, which we call the activity graph. So in here, every element represents a dedicated animation. The activity animations are represented as graph states in red, and transition animations, as well as graph transitions, these are the yellow arrows. These activity graphs are part of the behavior place definition. They are created by the animators. So at this point, you may look at where we are and think, okay, Jacek, so you had 50 animation graphs, which was hard to maintain. And to fix that, you packed them all into one Uber animation graph, which may still be configured by 50 different graphs. Like what? How is that better? Now let me give you one more example. Here we've got a state machine which contains two activities. This is our shopkeeper from before. It's either sitting or trading with us. Now let's imagine that the shopkeeper sometimes falls asleep in their chair, right? Don't we all? We may represent that using another activity called sleep, with dedicated transitions to that activity. And in the old approach, we would have to create this state machine, which would probably be used in like one place in the entire game. And what if we wanted more activities? What if each activity could transition into any other activity? And we found the state machine to be too complicated and error-prone. We needed a better way to represent it. And with the activity graph, we can extend our previous configuration with the new activity and adding the proper transitions. This type of graph is much more constrained than the animation graphs. For our purpose, animation graphs had too many moving parts, and so activity graphs became easier to create and maintain. It is also much easier to validate and analyze this structure, which also became crucial for us. And I'll come back to that later. Let's summarize this part of the talk. During production, we managed to create a common state machine for all of the behavior places in the game, which is configured with lightweight activity graphs. These graphs allow us to express the state machine on a higher level and to minimize the memory footprint. Also, traversing a common simple structure is easier to track and replicate to other network peers. We've also managed to decouple the behavior structure from the content, which made it easier to collaborate and create new assets. During production, we've created thousands of activity graphs, which gave us the variety and the scalability that we were looking for. Now that you know how the state machine is built and what kind of animations are used in each state, I'll talk a bit more about the constraints that we've imposed on the animation content. We'll cover behavior place versus AI positioning, root motion, and navigation issues. Let's look at this simple example. Here's the character approaching a chair to sit on it. There are two major poses in here, standing and sitting. With the entry animation, we can go from standing to sitting. All right. However, before we start the entry, the character must approach a certain point in space. So what is that point exactly? Let's simplify our view a bit. On the slide, you can see a blue line, which represents the nav mesh, and a black thing that represents a chair, which sits outside of the nav mesh. And now we can break the action down into two phases. First, we employ our movement behavior to reach a certain point. Boom, boom. And then we use the behavior place to do the interaction that you saw in the video. Now, remember that the character can travel only as far as the nav mesh goes using the movement. And then it must start executing the entry animation, during which they also move towards the chair and also leaving the nav mesh. Okay, but what if the chair was moved further away from the nav mesh? What if it was rotated differently? If we execute the animation too soon or too late in space, we will not match the chair position. So should the level designer move the chair closer? That's a lot of tedious work. So should we do that automatically? But then how do we validate that? And should we add more fake and natural motion to the character to make it match the chair, simply correct it? Or maybe the chair should always be placed on the nav mesh. But then it becomes a problematic obstacle when it is not used. What if the entry animation changes to cover less distance? Do we have to move around all the chairs that are already placed on the level? As you can see, the problem is not as simple as it previously seemed. So let's see how can we solve it. Let's look at a situation from the top and simplify our view again. With that symbol on the left, we represent the behavior place entity. For now, it's just a point in the direction in the horizontal plane. And whenever AI wants to enter the behavior place, that's the only point that we've got. The character walks up to it and then starts the entry animation. And at the end is where the activity starts. Everything must match. We can see that the chair position is correct because it will match our character's First, this gray line shows the root motion trajectory for the entry animation. At the end of it is where the activity starts. Now we can see that the chair position is correct because it will match our character's sitting pose. However, with this setup, level designers have two variables to account for. They must place both the behavior place and the chair on the scene, and they need to be placed relative to each other perfectly. And if the entry animation changes, one or the other must be moved around. So, of course, this is too error prone, and this is a huge maintenance burden. We had to improve it. To fix it, we figured out a different solution. What if we place the behavior place exactly where the chair is? The entry animation should now end at the behavior place position, which is synchronized with the position of the sitting. And to do that, we must calculate the point in world space where the AI is supposed to start the entry. And we call these entry points. They are calculated from the animation root motion and saved in the behavior place definition during asset compilation. Now let's add nav mesh to the mix. The entry point lies on the nav mesh, so the AI will be able to navigate to it and then start the entry. And for situations where that is not the case, we've implemented a validation process which reports unreachable entry points to level designers. And their task is now simplified to simply placing a chair wherever they like, placing the behavior place at the exact same spot. This can be automatized, and making sure that the entry point lies on the nav mesh. Of course, the entry animation can still change in such a way that the whole behavior place can become unreachable without the level designers knowing about it. However, this situation is much easier to detect than the characters sitting in the air or them being completely desynchronized with their environment during behavior place execution. There's another bonus to this approach. We can now have multiple entry points in the activity graph. For example, one for approaching the chair from the left, one from the right. We simply calculate entry points separately for each one. And with this data at hand, AI can now easily pick which entry point it would like to use to best approach the chair, based on the distance to the point or its orientation. Also, if one of the points is unreachable, we can simply pick another one. It is worth mentioning here that to aid level designers in the placement, we've implemented an isolated AI simulation in the editor. It's what you've just saw in the video. This turned out to be an extremely helpful tool, and you can preview the AI enter the behavior place, the chair animating, and the calculated entry points. Let's look at a different, more complicated example with multiple activities. So in this place, we've got 5 activities. Each one is playing a simple idle standing animation. And in the video, we can observe the transitions and the calculated entry points. And as the behavior place runs, the character decides to move from one point on the activity to a point of another, and it will always move through the middle activity, just like it is defined in the activity graph. This is how it looks like in this example. So starting from the center activity, we can step in 4 directions to 4 other activities: front, back, left, and right. And from each one, we can step back to the center. There is no entry and exit animations from stand to center, since there is no need for a standing to standing animation. We can simply blend in there. Let's recap. The simple structure of activity graphs allows us to extract root motion data from the animations during asset compilation. And on the level, we set the stage in such a way that the entry animations start at a pre-calculated entry points and then lead to the activity point, which may be outside of the nav mesh, unreachable otherwise. And exit animations mirror entry animations and must lead the character back onto the nav mesh. With multiple activities, transitions may lead to different activity points, but we must validate that the root motion of transition from A to B must be an inverse of the motion from B to A. Otherwise, the whole system would float around the level after a few loops. We also made sure that the level designer's work is as easy as possible by implementing some visualization tools in the editor. Now that you know how we position the entities, let's talk about animating objects and interacting with the environment. We'll look at different types of meshes animated in the behavior place and how we set them up. First, we'd like to go back to our example with the chair and extend it. We want to increase the feeling of interactivity between the character and the chair. So we'd like the character to grab the chair first, move it back a little, and then sit on it. So the animation is changed, it's imported into the engine, but now it has additional data for the movement of the chair. And let's call that the chair root motion. And how do we make use of it? First, every definition asset contains metadata about the animations. We know that in this chair sitting scenario, the chair is now animated. So the animator adds that information to the definition. They define a generic name for the animated item, like the chair, and the name of the special animation track that I mentioned before, the chair root motion. But the second piece of information is given to us by level designers. Knowing that they also now know that they need a chair to animate properly, they must save a reference to the chair entity in a special list inside the behavior place entities, so one entity knows about the other. And when the character executes behavior, we simply use those both sources of information. We tell the animation system to take this transform that is called chair root motion and apply it to the chair entity pointed to us by level designers. So this is what we call a bound animated mesh, because an actual entity binds to a declaration made by the animator. Okay, so what can go wrong here? Let's imagine that in the first frame of the animation, the chair position is slightly different than how the level designer placed it on the level. So it's our previous problem once again. And if that's the case, the chair will be teleported to the position from the animation, and you saw that happening in the video. So what do? Remember the activity graph I mentioned earlier? The same process that compiles it also saves the initial transforms of all motion tracks. For example, our chair root motion, and this is what we call a mesh point. And we use that data during word spawning to reposition the chair mesh. Thanks to that mechanism, characters always smoothly interact with the objects. There's no teleporting, no sliding, and everything is aligned correctly. However, Sometimes we cannot move the bound mesh from its original position. Take these doors, for example. Let's imagine they are placed in the door frame, and we only want to rotate or animate some parts of them. Here, the doors are opened for the time of the behavior place execution and then closed again at the end. And for such cases, we can define an animated mesh to be an anchor. Coming back to our previous example with the chair, if we place the behavior place entity right there and connected this chair to it, the chair would align itself. And with anchored anim meshes, we do something different. Using the calculated mesh point, we shift the entire animation space so that it matches the anchor entity. Now the whole activity graph aligns to the anchor, and it does not matter where the behavior place entity is placed, because now the anchor mesh is the reference point for the entire activity graph. So here's another demo with the doors. We can move around the entity, but the animation space stays anchored to the doors. And by the way, this is the editor visualization that I told you about before. However, not all meshes must be placed on the level. So imagine if we had to place every hammer, every screwdriver, cigarette, or any small item on the level. That would be too much work. That's why for small items such as these, animators can also define what is called a spawned animated mesh in the behavior definition. And for such definitions, we spawn a mesh when the behavior starts and despawn it at the end. Simple. Other than that, we use the same motion track mechanism to animate them. Okay, let's summarize. When creating the behavior definition, animators give us additional metadata about the required animated meshes. So selected entities bind to the animator's definition, and they are fully controlled by the behavior place. Meshes which are unmovable are defined as anchors, which aligns the activity graph to their position without moving them. Additionally, small meshes which are not part of the environment can be spawned for the duration of the behavior. It's now time to summarize this talk, share some lessons learned, and our plans for further development. In this talk, you've learned about behavior places in CEngine. They are the building block of many different locations in Dying Light 2, Stay Human. They ended up being used as part of hubs, bandit camps, open world encounters, dialogue slots, spawn points. It's a scalable technology by which animators create location-specific behaviors to be placed by level designers. The system allows for massive variety in behaviors with only little impact on performance. It allows our characters to interact and become part of the environment. It was designed for high precision in motion and positioning. We achieve that using custom compiled asset types and by analyzing animation motion data. Here are the most important things we've learned. So all content must strictly be validated if you want to achieve high precision. We've had cases where there was only a tiny amount of root motion in the looped activity animation, which caused the entire animation space to rotate 90 degrees after a couple of minutes, after a couple of loops. Also, to achieve great performance, you must use offline processes. We could build the activity graph during the game, but we would need to load 5 animations just to sample a few transforms. Also, especially tailored tools for content creators are extremely important. So you can create the best, the smartest feature, but without the appropriate tooling, it may become useless. The tools can show content creators what the possibilities are and automate mundane tasks. Lastly, make sure to always iterate the system with the users. With behavior places, we went through 3 major iterations to get there. And as always, try to keep things simple and avoid over-engineering. Let's close with our plans. We'd like to have a single behavior place that can animate more than one AI. We will be also focusing on traversal using behavior places, which we've managed to accomplish in some quests already. And with managing the animated meshes, we would like our AIs to be able to pick up an item in one place and put it down in a different one. And that's all. I'd like to invite you to our Techland's booth. There's a lot of people from all the departments chilling there. There's like 90 of us. So if you'd like to join us and work on some new cool things, or maybe you would like to just chat for a bit, there we are. And I believe we've now got time for some questions.
Okay. Thank you, Jacek, very much. And do you have any questions? Yes. Okay.
Do you have different sizes or shapes of skeletons? For example, if a different character uses the same chair, did you have to set up different entry points, or how did you manage that?
Yes, so we support different skeletons in a single behavior place by a feature that's called variants. It's just a grouping feature. We have each behavior place can have a variant for any other skeleton. And so then it is the animator's responsibility to make sure that the motion that comes from both variants is the same or almost the same, so that the things still match up. And when it comes to like chair sizes, that's a whole different story.
Okay, thank you.
Thank you. Anybody else? Okay.
I have a question about the bound animated mesh.
Mm-hmm.
Can it be used in multiple behavior places? Or is it one bound animation mesh for the one behavior place?
It is possible to bind the animated mesh, one mesh to both two behavior places, but that is considered an error currently. So we validate against that. And so yeah, you shouldn't do that. You can have two meshes, but there wasn't really many cases where that could be problematic, especially since we added the variance feature. So we could have multiple characters, well, not at the same time, but different characters use the same behavior place.
Okay, and what about spawned meshes? Like there is no problem like from the NPCs to get them like from the own inventory or something?
Yeah, so the trick is that spawned animated meshes, they start existing at the behavior start, and then they are despawned. And the trick here is that, for example, the character can, if it's about the screwdriver, the character can do like this quick sleight of hand motion and just take the screwdriver out of his own body, and it's really not visible, so you don't have to micromanage every item. It's just we hide them behind, nobody sees that, and we despawn it that way.
Are there any bigger spawned items, like, I don't know, the axe or something like the chainsaw that was in the part of the video? Yeah,
so in the video you saw the gameplay. So at the beginning with the chainsaw and the combat, that's not handled using behavior places. But if you'd like to use a bigger mesh as a spawned animated mesh, yes, you can do that. You still can, fit an axe into the body and just magically, pop it into existence if that's what you need. But in general, we recommend animators to use the bound animated meshes if that's, bigger than a screwdriver or something that you can hide in your pocket. It should be a bound animated mesh, not a spawned one.
Okay, thank you.
Good questions.
Thank you. Okay.
Yeah, thanks for the great talk, actually. I had a question. All of your examples of your behavior places started from a standing idle.
Mm-hmm.
is that the case for all of the game, or did you have different idles? And if so, how did you expose that information to the navigating system?
Okay, so with most the behavior places, it was enough to use the standing pose as this initial pose, but there is a way to start from a different pose. It's fine. It's all saved in the entry points. So there is an API for accessing the entry points of a particular behavior place, and the code can select that, and it can select the entry point which is closer, and it can select the entry point that starts from a different pose, if that's what you need, right?
Yeah, kind of. Yeah, basically, yeah. But did you because I mean, just naively thinking going up to a position and standing and then moving again is quite robotic. So did you ever try entry points that are in motion to try and create a fluid? Yes, transition?
That's a great question. You can enter the behavior place preserving the motion, but we've kind of fallen back onto the movement behavior so that the movement does not really stop, and then we kind of blend the movement with the entry. And if you prepare the animations just right, you will be able to achieve a pretty smooth entry into the behavior place. We did that in the initial quests in the prologue of the game, and then the quests, escort quests with Hakan. You can take a look at that. There's some really nice examples of that. It's not perfect, but we are really happy with how it turned out in the end.
Fair enough. Thank you very much.
Thanks.
Thank you very much. Okay.
Yeah. Hello. So can this behavior place's position or any transform be changed at runtime?
Well, yes. Actually, we've implemented that. So if you parent the behavior place to anything that's movable, it moves along with it. No problem with that. There was some need for some custom tricks to make that work, but it basically worked out of the box.
Okay, and so the validator for nav mesh on whether or not NPC can handle it, it is then revalidated at runtime?
It's not actually. It's up to the level designers and the animators to make sure then that this particular path that the movable object takes is correctly managed, right? So it needs to be broken down into a few steps. You need to stop the movable objects, then go into the behavior place. You can then start moving, then it has to stop, and then you can leave the behavior place, and then it works.
Okay, so when it comes to player interacting with chairs by moving it with a grenade or something, would that be possible to then revalidate the entry point?
Great question. It is possible. We didn't have the need to implement that. Yeah.
Okay.
But it could be possible. Yeah.
All right.
Thank you. Anybody else? Oh, okay.
Thank you for the talk. Did you have any support for using animations, to have some animation to be used on several meshes? Do you handle it biometrics, or do you have some other adjustments to adjust the card animations to match the meshes, depending on what they are having? So you can use this one animation in many places, so it's easier to budget it.
Yes. So I'm not aware of such metrics for AIs. There were, of course, metrics for players, but I wasn't, the complete part of this process. So maybe there was. I didn't really. Yeah, my friend is telling that there were some metrics. So yeah, of course. But because if you had 100 different chairs, then the animations would not match pretty well to most of them. So yeah, you really need to take care of that as soon as possible to make it match and not to duplicate animations, because this chair happens to have no leg, right? I don't know.
Thank you.
Thank you.
Hello. Thank you for the talk. Very interesting. Do you have a fail-safe if, for example, the player interrupts this behavior. So can this NPC be knocked over from the chair, or can this door that you've shown be blocked, and then the NPC knows this and can react to it somehow?
That's a great question. And in general, interrupting behavior places or the behavior places ending their behavior by itself is, I think, the topic for the next talk, because it's there's so many different problems with that. In general, yes, behavior places can be interrupted, but it also depends on on the definition. Basically, the definition, the animator tells us, okay, can this be interrupted? Because if there is no animation of let's say standing up quickly from the chair, then we mark it as non-interruptible. But if it's, for example, we had a lot of behavior places in the bandit camps in the open world, and so they all had to be very responsive and always be able to react quickly. So it kind of depends on the content. You need to limit yourselves a bit for the responsiveness, and the configuration must be right for this content.
Thank you very much. That's all? Okay.
Sorry for keeping you guys. Hey, got a question.
Okay.
Because your approach to placing all those entry spots is very animation centric, because you place the spots first and then you place it on a level. In the case where like there are two entry spots close to each other, in the situation that NPCs can choose those nearby places, how did you secure it so that they didn't clip to each other? Did you have any system that prevented them from using if they're standing close to each other, or was it just level designer job? Don't place it.
Very
like
good
this.
question. When it comes to a single behavior place, it is guarded for being used by one AI, of course. But when it comes to multiple AIs on the same multiple behavior places in the similar place close by, this was the level designer's job. This is, however, to be improved, of course.
Okay, thank you.
Thank you. Okay. I think that we can finish. Thank you very much, Jacek.
Thank you.